Talk about big. This unit we've been covering is really big for your chemistry studies. So let's review. But first, let me get back to normal. Ah, yeah, that's better. Well, so far, you've learned how to write chemical formulas from chemical names, how to write names from formulas, and how to balance chemical equations. You even know how to take a word equation and translate it into a chemical equation using symbols and formulas. What could be left? Well, how about learning to predict the products of a chemical equation and then identifying the reaction as to the type it is? Or how about learning how to indicate the physical state of a substance in a chemical reaction? Oh yes, there's still much more to this simple balancing act.
In this program, you will learn to indicate the state of the substances in a chemical equation, identify the major types of reactions, and learn how to predict the products of a chemical reaction when given the reactants.
You have seen that a chemical equation shows what substances take part in a chemical reaction and the relative number of atoms of each element in the reaction. But chemists also may choose to give even more information than what you've previously learned about. For example, the states of the substances, whether they are solid, liquid, or gaseous, may be indicated in a chemical equation. Chemists are also able to indicate if a substance is aqueous, which means it has been dissolved in water. Let's see just how a chemist goes about giving this additional information when writing a chemical equation.
Chemists often use abbreviations to be even more descriptive of a chemical reaction. You need to know these abbreviations so that you will be able to properly read a chemical equation, and you will also be able to include these abbreviations in equations you're writing. You need to make sure that you write these abbreviations in parentheses and that you write them right after the symbol or formula of the substance they're describing. First of all, the states, solid, liquid, and gas, are easy. Remember that state just refers to the form in which you find a chemical. You use an S to represent the solid phase, L to represent the liquid phase, and G to represent the gaseous phase. AQ means that a substance is aqueous, meaning, as I just told you, that a substance has been dissolved in water. Be sure that you don't confuse a substance that is aqueous with a substance that is a liquid. Mercury is a liquid at room temperature, which is very different from being dissolved in water.
How can you tell the state of a substance so that you can use these abbreviations when you're writing an equation? Well, sometimes the word equation tells you. For example, if you're told that a substance is a vapor, that's the same thing as it being a gas. We usually use the word vapor for the gaseous state of a substance that isn't a gas at room temperature. For example, water is a liquid at room temperature, so we refer to its gaseous state as a vapor. Oxygen is a gas at room temperature, so we refer to its gaseous state as just that, a gas. If an equation indicates that a substance is dissolved in water, that means it's aqueous. The periodic table will help you too. Remember that you indicated on your periodic table the state of the elements at room temperature. And some chemicals you know the state of simply because they're so common. For example, you know that you breathe out carbon dioxide, a gas. And you know that sodium chloride, table salt, is a solid at room temperature. But you still need some additional guidelines for those substances that aren't so familiar. Get your notebook ready because you need to write these down.
Remember that many of these guidelines are simply a rule of thumb. We learned earlier that a rule of thumb may have exceptions and won't always work, but it's a guideline nonetheless. All metals are solids except for mercury, which is a liquid. Most nonmetals are gases except for bromine, which is a liquid, and these exceptions that are solids at room temperature: carbon, phosphorus, sulfur, selenium, tellurium, and astatine. All metalloids are solids. Assume, unless told otherwise, that all ionic compounds are solids. Although there are many exceptions, assume that all covalent compounds are liquids, unless told otherwise. Here's where our rule of thumb certainly doesn't always work, but it's better than no guideline at all.
Now, it's time for you to try your hand at writing a chemical equation, including symbols, or abbreviations, to denote the state of the substances. Consider this sentence describing the following chemical reaction. When heated, solid mercury 2 oxide yields mercury and oxygen gas. Take a few seconds to write the correctly balanced equation, being sure to include abbreviations indicating the state of the chemicals. Here's the answer. Mercury 2 oxide is an ionic compound because it is composed of a metal, mercury, and a nonmetal, oxygen. According to our guidelines, ionic compounds are solids. Mercury metal is a liquid, which is an exception to the fact that most metals are solids at room temperature. And oxygen is a nonmetal, which is a gas at room temperature. I hope that writing the formulas and balancing the equation was easy for you. If not, you need to go back to your notes from earlier lessons in Unit 6 and review. These are skills that are extremely important. I can't emphasize that enough because you'll use them throughout your chemistry studies. You can't simply skip over them. Remember that chemistry builds throughout the year. Your local teacher will have lots of practice for you, but first, I want to teach you how to classify chemical reactions and predict the products of a reaction. This is a significant part of chemistry. You'll see that there are a number of ways to classify chemical reactions, but we're going to focus on 5 different classifications. Let's get started with one of the simplest, synthesis reactions.
Synthesis occurs when 2 or more compounds or elements are combined together to form a new compound. An example of synthesis is the combining of hydrogen and oxygen to form H2O, or water. This can be done by burning hydrogen gas in the presence of oxygen. As the hydrogen burns, hydrogen molecules combine with oxygen molecules to form water, and heat energy is given off. The world's great oceans are witness to the fact that at one point in the Earth's history, tremendous clouds of burning hydrogen combine with atmospheric oxygen to form water vapor that condense to fall to Earth as rain, filling the low-lying basins of the Earth.
Do you have your pencil and paper handy? It's definitely time for some notes as you learn to identify the 5 main types of chemical reactions.
The first type of chemical reaction we'll study is called a direct combination or synthesis reaction. In this type of reaction, 2 or more substances combine to produce a more complex substance. This reaction takes the general form A plus B yields AB. When iron and sulfur combine, the compound iron 2-sulfide is formed. This reaction follows the general trend of a synthesis reaction, in which 2 or more simpler substances combine and form a more complex substance. In other words, it follows the general trend that A plus B yields AB. This is also classified as synthesis because it follows the pattern of two or more simpler substances combining to form a more complex substance. In this reaction, water and sulfur trioxide combine to form hydrogen sulfate or sulfuric acid. Because sulfur trioxide is a common pollutant, can you see how acid rain forms?
Synthesis reactions are sometimes called direct combination reactions because, as you can see, the reactants combine to form more complex substances. Just look for the general A plus B yields AB format when identifying a synthesis reaction. Let's look now at another type of reaction, decomposition.
There are substances that, unlike water, can be decomposed by the application of heat energy rather than electrical energy. An example is the reddish-orange solid mercury oxide, which, when heated, decomposes into its component parts, mercury and oxygen.
As you just saw, decomposition reactions are the opposite of synthesis reactions. During decomposition, one substance breaks down to form two or more simpler substances. Decomposition reactions have the general form AB yields A plus B.
In a decomposition reaction, a compound breaks up into its constituent elements. Let's put a couple of examples of decomposition reactions in your notes.
In a decomposition reaction, the opposite of synthesis occurs. One substance breaks down into two or more simpler substances. For example, when water decomposes or breaks down, it yields the elements hydrogen and oxygen. Another decomposition reaction takes place when mercury 2 oxide is decomposed by heat. The delta symbol over the yield sign shows that the reactant is heated. This is yet another way that chemists are able to give lots of information about a reaction in a shorthand manner. Notice, too, that there is a vertical arrow beside the symbol for oxygen. An upward pointing arrow is another way to indicate that the substance leaves the reaction as a gas.
We've looked closely at a decomposition reaction, and you've seen that these reactions are easy to recognize. I'm sure you remember from biology that when something decomposes, it breaks down. So just look for the general form of AB yields A plus B in order to recognize a decomposition reaction. Now let's check out a type of reaction referred to as a replacement reaction.
There are two types of replacement reactions, single replacement and double replacement. Both types of replacement reactions generally occur in water-based solutions. A single replacement reaction occurs when one element replaces another in a compound, forming a new compound. A typical example of a single replacement reaction occurs when a magnesium strip is placed in a solution of hydrochloric acid and water. Hydrochloric acid is an ionic compound that separates into positively charged hydrogen ions and negatively charged chlorine ions in water. Ions are atoms or compounds that have a positive or negative charge as a result of gaining or losing one or more electrons. If an atom or compound loses an electron, it becomes positively charged. If an atom or compound gains an electron, it becomes negatively charged. The positive hydrogen ions of the hydrochloric acid acquire electrons from the magnesium atoms that make up the magnesium strip. As a result, the hydrogen ions become free hydrogen atoms again, as they no longer have a positive charge holding them to negatively charged chlorine atoms. The free hydrogen atoms bubble to the surface as hydrogen gas. The magnesium atoms which have given up their electrons become positively charged and tied to the negatively charged chlorine atoms, replacing the hydrogen atoms. At the end of the reaction, no solid magnesium remains, as the magnesium ions replace the hydrogen ions in solution.
You just saw that single replacement reactions occur when a less active element in a compound is replaced by a more active element. These reactions have the general form A plus BY yields AY plus B. In this example, A is more active than B, so A replaces B in the compound. Consider the following reaction. When hydrogen gas is needed in the lab, the reaction of zinc and hydrochloric acid is used. The equation is written Zn plus 2HCl yields ZnCl2 plus H2. Notice that the reaction tells you the state of the substances taking part in the reaction. The zinc is a solid. The hydrogen chloride and zinc chloride are dissolved in water, and the hydrogen is a gas. Before the reaction, atoms of zinc are in the elemental state, while atoms of hydrogen and chlorine are combined in a compound. After the reaction, atoms of hydrogen are in the elemental state, and atoms of zinc and chlorine are combined in a compound. In this single replacement reaction, the more active zinc replaced the less active hydrogen. In other words, zinc and hydrogen simply switched places. If a piece of aluminum is placed in a solution of copper 2 chloride, the aluminum replaces the copper in the compound, producing aluminum chloride and copper metal. The more active metal, aluminum, replaced the less active metal, copper. Aluminum and copper simply switched places, and a single replacement reaction took place. Make sure you're paying attention to the states of the substances indicated in the chemical equation. Remember that S means the substance is a solid, and that AQ means the substance is dissolved in water. Just because an equation for a reaction can be written, it doesn't mean the reaction will actually occur. An activity series must be consulted to determine if the element that is to do the replacing is more active than the element that it's to replace. An activity series is an arrangement of elements in the order of their tendency to react. By using an activity series, you can predict whether a reaction will occur.
This is an example of a simple activity series like the one in your note-taking guide. Generally speaking, any element can displace those elements that are below it in an activity series, but not those above it. In the previous example, aluminum was able to replace copper because it's above copper on the series, meaning that aluminum is more active than copper. But what about this reaction? You could write an equation for the reaction of copper plus magnesium chloride, but look at the activity series. Copper is below magnesium, meaning that copper is less active than magnesium. The reaction does not occur. That's why we write the letters NR after the yield sign. No reaction.
To review, a single replacement reaction takes the general form of A plus BY yields AY plus B. An element plus a compound yields an element plus a compound. Remember, though, that an activity series is necessary to predict if a reaction will actually take place. A more active element will replace a less active element in a compound, but a less active element won't replace a more active element in a compound. Our next reaction type is also a replacement reaction, but this one is a double replacement. Let's watch.
In a double replacement reaction, two compounds that separate into positive and negative ions in solution switch partners and form two new compounds. Both sodium chloride and silver nitrate form clear ionic solutions when added to water. However, when the two ionic solutions are mixed together, they switch partners. One of the newly produced compounds, silver chloride, forms solid particles called precipitates that eventually settle to the bottom of the reaction container because they are denser than water.
In a double replacement reaction, the elements in an aqueous solution of reacting compounds replace each other. In other words, the positive ions and negative ions exchange partners. These reactions are also called metathesis reactions, which is Greek for to transpose. This reaction takes the general form of AX plus BY yields AY plus BX. When a colorless solution of potassium iodide and a colorless solution of lead-2 nitrate are mixed, a fine yellow powder forms, lead-2 iodide. The other product of the reaction is dissolved potassium nitrate. Because the lead-2 iodide won't dissolve, it is said to be a precipitate. That's an important vocabulary term, so be sure you get it down in your notes. Sometimes, instead of the abbreviation S, which denotes that a precipitate is a solid, an arrow pointing down will be used. Notice that the positive lead and positive potassium ions simply switched partners in our double replacement reaction. Let's take a look at another double replacement reaction between aqueous sodium chloride and silver nitrate. In this reaction, too, the positive ions switch places. So the products are sodium nitrate, which is soluble, and silver chloride, which is not soluble. Notice the arrow pointing down. Remember, this is another way to represent the fact that silver chloride is a precipitate, or insoluble solid.
To review, double replacement reactions take the form AX plus BY yields AY plus BX. Again, notice that A and B, the positive ions, have simply switched places. Normally, double replacement reactions occur in an aqueous solution, and unlike single replacement reactions, an activity series doesn't determine whether the reaction will occur or not. Hang in there with me. You're almost through for the day. However, we do have one more reaction type to identify. Combustion.
Combustion reactions usually give off a large amount of heat and light. Combustion, normally called burning, involves a substance combining with oxygen from the atmosphere. An important combustion reaction is that of a hydrocarbon. Recall that hydrocarbons are compounds that contain only hydrogen and carbon. In a complete combustion reaction, hydrocarbons combine with oxygen to produce carbon dioxide and water.
Although combustion is the term for the burning of any substance, we're going to focus on the combustion of hydrocarbons. Let's look at a couple of examples.
Propane, C3H8, is a gas used for cooking and home heating. Propane burns in air, producing carbon dioxide and water. If there isn't enough oxygen present, carbon monoxide also is produced. That's why some of you may have carbon monoxide detectors in your home. Carbon monoxide is a colorless, odorless, and poisonous gas. A carbon monoxide detector will alert the homeowner that their home furnace isn't functioning properly, producing carbon monoxide, a potentially lethal gas. If there isn't enough oxygen present and carbon monoxide is also being produced, the combustion is said to be incomplete. However, complete combustion occurs when there is enough oxygen present, and the only products that result from burning the hydrocarbon are carbon dioxide and water. Another example of hydrocarbon combustion is when methane burns. Methane, CH4 plus oxygen gas from the atmosphere, produces, you guessed it, carbon dioxide and water.
You've put it all together now. You've learned how to use abbreviations to denote the physical state of a substance in a chemical reaction, and you've learned how to classify 5 main reaction types. Since you know how to classify chemical reactions, you could even predict what the products of a reaction would be. Your local teacher will give you lots of practice before your test. But before I go, let's take our chemistry quiz.
We'll begin today's quiz with a question about bonding. Cumulative review question number 1 is, when 2 atoms share 3 pairs of electrons, the bond is called a single bond, B, double bond, C, triple bond. Cumulative review question number 2 goes back to our last program. The starting substances in a chemical reaction are called the A, products, B, yield, C, reactants, D, coefficients. Now it's time to start reviewing today's material. We'll see if you were paying attention. Question number 1. The abbreviation used to represent a gas in a chemical reaction is AG, B, AQ, C, an arrow pointing upward, D, both A and C. Question number 2. The complete combustion of a hydrocarbon produces A, carbon dioxide and water, B, carbon monoxide and water. Number 3. The general form of A plus B yields AB represents what type of reaction? A, single replacement, B, double replacement, C, synthesis, D, decomposition. Number 4. When predicting the products of a single replacement reaction, if an element is below another element in an activity series, the element placed lower will not replace the element placed higher. A, true, B, false. And now for your last review question of the day. What do we call a product of a reaction that is an insoluble substance? A, metathesis, B, hydrocarbon, C, precipitate, D, neutralization.
I hope you did well on your review. You'll be taking your unit test soon, so try to put it all together. I'll see you next time when we begin to discuss that pesky mole. Oh, hi there, little fella.